Hey. All right, Mr. Klinkerman, we are on a part 2 of our lesson in section 7.7, in which we're trying to learn how to find relative extrema. We're learning other methods for doing that. And actually, in learning goal 2, we're trying to learn how to find the absolute extrema of a function on a closed interval. All right, and it turns out this isn't the point of the lesson that we're watching right now, but it is important. We're going to dive a little bit into this whole thing where you can apply techniques for finding extrema to solve optimization problems. So our focus is learning goal 2. We're going to include a little bit of learning goal 3 for this section within this video. Well, let's get on to finding the absolute extrema of a function. Okay, now you guys are used to looking at functions and considering them on the domain from negative infinity to positive infinity. All right, that's the domain that we've been looking at with every function that at least could include that domain. Now there's been breaks in them, but nevertheless, that could be a function like this. And almost every time with the functions we've been looking at, it was not very useful for us to talk about the absolute maximum and minimum values of the graph, because the absolute maximum and minimum values were negative infinity. All right, you see this one goes down forever, or positive infinity. Now, we spent a lot of time trying to find the relative maximum and relative minimum values because those were such important features on a graph, but the absolutes were not very useful. Now, we did have some exceptions to that. It would have been useful for a graph such as this one, for instance, to talk about the absolute minimum value anyway, because it wasn't negative infinity. The absolute minimum value occurred at that critical value, but the absolute maximum value went to positive infinity. All right, what we're going to start doing in this lesson, though, is we're going to start looking at a certain portion of the domain rather than at the entirety of the domain of a function. And so let's say I were to divide this first function into this portion right here. And it's just began and ended at those 2 points. Well, when you restrict the domain, there is a point on the interval that you're looking at that is the absolute highest and the absolute lowest. And I think you can imagine that right there. There is an absolute maximum and absolute minimum on that interval. And so that's what we're going to look at, is how do you find on a closed interval the absolute extrema. All right, let me draw a couple more pictures here to illustrate what I'm trying to say to you. Let's say that this is a portion of the graph of a function that we were trying to look at. And what we're going to be doing is pretending we have functions that are on the interval between two numbers a and b. So this is where x would be equal to a. This is where x would be equal to b. And you can tell on that interval that there is an absolute maximum and an absolute minimum value. All right. Now, for this particular graph, you can see that the absolute minimum value occurs at a, and the absolute maximum value occurs at b. And certainly, it's possible for the absolute maximum and minimum values to occur at the endpoints of such a graph, but they don't have to. Consider this graph. All right, you can see on this graph, if I'm going from A to B, that the absolute maximum occurs at one of the critical values, and so does the absolute minimum. And then, of course, it's also possible that you can get a situation where you have a maximum occur at one of the endpoints and a minimum occur at one of the critical values, or vice versa. The major point here, let me go ahead and draw that. All right, you see the absolute maximum at the beginning, absolute minimum there at one of the critical values. When you're trying to find absolute extrema, you look at either the endpoints A and B, or you look at the critical values to find those maximum and minimum values. All right, think you've got that down, but I want to give you a few guidelines just to ensure that. Whenever we're talking about finding the absolute extrema on an interval from A to B. It's important that you realize the lowest and highest numbers in the domain that you're looking at. Here's the way that works. The first thing you have to do is you have to find any critical values of the function on that interval, because the maximums can occur at those critical values. And then the second thing you need to do is you need to realize that the extremes can occur at either the endpoints or the critical values. And the way you determine where those extremes are is by evaluating the function at its endpoints and at any critical values between the endpoints. Okay, so if you're looking on the interval from 0 to 5 and there's a critical value at 2 and 4, you've got to plug in 0 and 5, the endpoints, into the function, as well as 2 and 4, the critical values, into the function, in order to figure out where the absolute max and the absolute min are. All right, let's try that out. It's really pretty simple. We're going to find the absolute maximum and minimum of the function that you see on the interval from -5 to +5. All right, that's our restricted interval. That's our A and B. We still are going to use the same principles that we've been using in terms of trying to find out where the relative minimum and maximum values are. We've got to find the critical values. And then you can either use the first derivative test or the second derivative test to find whether those critical values are maximums or minimums. Go ahead and find the first derivative, and only that if you want to use the first derivative test. If you want to use the second derivative test, go ahead and find that, and see if you can find out where the critical values are and whether they're maximum or minimum values. Now here's the work for the second derivative test. That's what I chose to use. I found that the critical value was at x equals -2 by setting the first derivative equal to 0. And then I plugged that critical value into the second derivative to see is the function concave up or down and at that critical value. And it turns out it was inconclusive. So if you decide to just use the first derivative test, you got lucky, and that was a little bit less work in this case, because now I've got to go back and use the first derivative test anyway. So let me draw my number line. Critical value at -2. And I'm looking at the signs of f prime of x. Well, if I plug in, say, -3, I'm going to get a positive value. Say I plug in 0, the first derivative is still going to be positive. So the function is always increasing here, meaning there is no relative minimum or relative maximum values. It's kind of one of those graphs that's it's going up all the time. Has a small place where the first derivative is equal to 0, but it's increasing all the time, so there's no relative maximum or minimum values. Okay, well, what does that mean for us? If there's no relative maximum or minimum values, that means that the absolute maximum and minimum values have to be at the endpoints. Okay, so our possibilities. The endpoints -5 and +5 could be where the absolute extrema lie. And I say that, normally you would also try the critical values, but there are no critical values here, so that's it. Our graph has to have absolute maximum and minimum values at the endpoints. Now we need to figure out which is a maximum and which is a minimum value, which, if you remember what I showed you about the function always being increasing, it's going to be pretty simple to do. That means the left endpoint has to be the minimum value. Nevertheless, I want to show you what you do in general. We plug in each of those endpoints into the function, and the critical values as well, if that were applicable, and we just see which gives us the largest and the smallest outputs. All right, f of -5 ends up being -216, where f of 5 ends up being 2,744. Well, pretty easy to determine which is the max and which is the min there. Our absolute minimum is going to occur when x equals -5. Our absolute maximum is going to occur when x equals +5. And the way you would write that then will be as you see right now. Fairly straightforward, right? Okay, we're going to try this in the context of a word problem right now. Check this out. Well, it's complicated, but it's not all that bad, actually. The problem says that the profit P in thousands of dollars for a company spending an amount S in thousands of dollars on advertising is given by the function P equals negative 1/10 S cubed plus 6S squared plus 400. All right, so we're dealing with profit P in thousands of dollars, and we're dealing with the amount spent on advertising S in thousands of dollars as well. And so this company, I guess, has figured out that they can calculate their profit based on the amount of money they spend on advertising. All right, pretty handy. Businesses try to do this kind of thing, actually. Now, there's a little bit more to the problem. It says that the company has an advertising budget of $70,000. That means they cannot exceed $70,000. We want to know what is the greatest amount of profit that they can get from that budget. Now, they can spend up to $70,000, but they don't have to spend the full $70,000, and potentially they could spend something less, maybe 10, maybe 20, maybe 40, maybe 60,000, and get a little bit more profit than if they spent the full 70,000. All right, there's this law of diminishing returns that's applicable here. Okay, so what are we trying to do? We're trying to do this. We're trying to find the absolute maximum profit they could earn on the interval from 0 to 70. Now, I know the advertising budget was $70,000, but remember that the profit and the amount S were also measured in thousands of dollars. So if we just put 70, that represents 70,000. Okay, well, let's do this. All right, we know that we need to find any relative extreme and any, relative minimum and relative maximum values on the interval from 0 to 70. And then we need to see what profit would come from those values, as well as what profit would come from spending nothing and spending the entire budget on advertising. All right, go ahead and find the first derivative and the second derivative if you like, and determine any relative extrema for this function. Now, I want to give you a little bit of help with the algebra on this one. I've written the first and second derivatives. Don't worry about the notation I used. You can still use P prime and P double prime of S. That's fine. But when we're setting this first derivative equal to 0 in order to find our critical values, I want to show you the factoring that I did because I'm factoring out a fraction. All right. You can see how S is a common factor for those two terms, and hopefully you can see how negative 3/10 would work as well. And when I factor out negative 3/10 S from negative 3/10 S squared, no doubt you see how that's going to yield an S right there. And also whenever I factor out a negative 3/10 S from a positive 12, you can see positive 12S, you can see how the S's will cancel essentially, and I'll have a minus. But what happens when I factor 3/10 out of 12? All right, well, if I factored 1/10 out of 12, it would give me 120. So if I factor 3/10 out of 12, it's going to end up leaving me with 40. All right. Now I'm going to double check with multiplication here just to make sure that that makes sense to you. If you multiply negative 3/10 with negative 40, it's going to give you a positive 120 over 10, and positive 120 over 10 is 12. So I've done that accurately. Now, that means that I get a critical value at S equals 40. And if I'm using the second derivative test to determine if that's a maximum or minimum value, then I need to plug 40 into the second derivative and see, do I get a positive or negative value? Well, negative 3/5 times 40 is negative 24, and negative 24 plus 12 is negative 12. So, I just found out that the second derivative is less than 0 at that critical value, which means that we have a scenario where the graph is concave down. We can say that we have a relative maximum value at x equals 40, or at S equals 40 in this particular case. Now, what we need to do is we need to determine is that the absolute maximum, or does the absolute maximum occur at one of the endpoints, 0 or 70? Let's test that out. Remember, what we're doing is we're plugging each of these values into the original function. All right, the two endpoints, 0 and 70, as well as the critical value that we found, 40. Now, if we plug in 0, I think it's fairly easy to see how you would get 400. And then let's use our graphing calculators to just go ahead and figure out what you get whenever you plug in 40 and whenever you plug in 70 to the function. And it turns out that whenever you plug in 40, you get 3,600. And whenever you plug in 70, you get negative 4,500. Now that's actually pretty interesting, okay? You can see that the highest of those values is right here. When the company spent $40,000 on advertising, they got $3,600,000, which is 3 million. Whoops, I meant to use a pen, not a highlighter to try to write that. That's the same thing as $3,600,000 that they made in profit if they spent $40,000 in advertising. Now, what I was referring to as interesting isn't necessarily that, but it's this fact right here. If they spent their entire budget that they cut on advertising, they end up losing money. Okay? So, that seems like a bad option for them. Our absolute maximum amount of profit ends up being $3,600,000. Now, if you go back and read the question, it wanted to know how much of the budget they should spend in order to maximize their profit. Well, they should spend $40,000 to maximize their profit. Okay, that's using AbsoluteExtrema, and that's actually optimizing. We found the maximum value for a real-world situation. We were able to optimize a function. All right, very good. See you in the next one.